So quick recap, I'm just going to say this again for anyone watching the video, even though I just said it to you guys. This is kind of my expectation for what I'm looking for in a skills journal question. As we learn new properties, add them to your list. So hopefully you guys all know how to find an x and y intercept. Today, let's do a little bit of review on domain and range, and then we'll do our new notes. So I'd like to go back to this slide right about here. Okay. Domain and range, we really need to start by talking about what a function really is. Okay? Yes, a function is a graph or an equation or a table of values, but there are certain things that we don't get to count as functions. Okay? And one of the reasons it might not be a function is because it does not have a one-to-one relationship. That's sometimes the words we use, one-to-one. And I used this as my analogy last day. 1 gives 2, 2 gives 4, 3 gives 6. Every number here literally goes to one value. But if I didn't point this out well enough last day, there's a huge problem here. 1 gives 2. That's great. But then later 1 gives 5. This is like an irreconcilable problem that is what would cause, say, like a computer code to crash. I cannot have 1 give 2 and then later give 5. It has to be one or the other. Does that make sense? And the silly analogy I had later in my notes would have been right here. Okay. If you were to go to the store and you want to buy something, if I were to say, okay, one thing costs $50, sure. 2 of them cost 95. Okay. 3 costs 83. But like, I can't have it that 7 items cost $56, but then later 7 items cost 55. Like, it has to be one or the other. You guys get the problem here? This is where you have a problem, and so these things are not considered functions. So I want to kind of show you over these last few slides that I skipped here more about functions, and then we're going to talk about how domain and range fits into this. Okay, so I think this is more or less where I kind of ran out of time last day. Is that right? This slide here. Why is this one a function? This one is a function. Why is this one a function? Every input gives only one output. This 1 goes to 2. This 0 also goes to 2. Is that okay, though? Yeah, that's fine. This 1 goes to 3, this 2 goes to 2, this 8 goes to 3. But let's say this 8 also went to 2. Now it's no good. So the analogy I like to sometimes use is a machine. When you put in one number, when you're done, you have to get back one number. Okay. I'd like to give you an example leading into quadratics, because that's where we're going to head today. Let's say that your function was to square a number. Let's say that I input the number 1, and then you squared it. What's your output? 1, right? 1 squared gives 1. So you would then say the point 1, 1 is on your graph. What if your input was 2? What does 2 give you as an output? 4. Can 2 also give 5, or 6, or 7? No, 2 literally just gives 4. But what if you input negative 2? Well, what happens when you square negative 2? You actually also get 4. So it's okay that the second number is the same. That's fine. But you cannot have the first number go to 2 different spots. Okay? One number in gives one number out. That's the rule of a function. Okay? So like that's why I have on this slide right here. It's kind of like a machine. And so far, the only functions you guys have worked with are linear functions. So if I were to give you the function 3x plus 10, then I should be able to give you any input, like say 17, and you'd be able to say, okay, 3 times 17 plus 10 gives me, and then you'd tell me the output, 61, I think. That makes sense? Okay. Well, I want to use an analogy to everyday life. I use this one a lot with my 30s. Okay. Think of a function being like a vending machine. Okay. How does a vending machine work? I have money. That's my input. I'm going to take money, I'm going to put that money in the machine, and I'm going to input a code. Like, say, a code could be Z16. Right? Then when I'm done typing that code and putting the money in, the machine does its stuff, and eventually I get an output, which is like a can of pop. Okay? Well, the analogy here is about the words domain and range. Domain refers to the inputs you're allowed to use. What sort of inputs can I type in? Now, for example, I wrote down here, code Z16 might not be valid because there literally isn't a Z16 option on the thing. Does that make sense? And so then the computer would then say, error, pick something else. Right? So as inputs, A1 works, B1 works, C1 works, ZWB457, that's not actually a valid input. Okay, so inputs are known as domains. Basically what this means is that what x values can you use? Now, most of the time when you're working with functions, you can use any x value you like. For example, let me go to this one right here. Can x be 5, 7, 32 over 55, pi? Unless you're shaking your head, sure, there's no problems. But this is not always true. Let's say that the function was this. Give me a sec here. We just did this in our last unit. Let's say that the function was 3x over x plus 1. Can I use 0? 3 times 0? That's 0. 0 plus 1 is 1. 0 over 1? Yeah, there's no problems there. Can I use 5? 3 times 5 is 15. 5 plus 1 is 6. Sure, that works. What's the one number I can't use? Yeah, we called those non-permissible values last unit. And this is now a good place for me to talk about that because there are sometimes certain inputs that are not valid. On this one here, you cannot try to input -1. It's just not possible. Does that make sense? That's your domain. So what you'd say is everything else is valid except for -1. Another type of function that you'll eventually learn, not in this course here, but like next year, is what if I gave you the function y equals the square root of x? Can you square root 7? Sure, it's a decimal number, but fine. Can you square root 93? Sure. Can you square root -5? So there's an input that's not valid. Back to my vending machine analogy here. This would be like certain codes that you can't input. So domain is what you input as x. Most of the time, though, we use this notation. Have you guys ever seen this before from me? It means x is an element of the reals. It's a shorthand way of saying basically everything. Okay? Real numbers basically account for most of the numbers we work with, minus like imaginary numbers, which we don't even learn about. So this means that x can be anything. Okay, well, outputs is what you get back. So I put in my money and I type in a code, and if it's a valid input code, then the machine then knows to give me back a Coke or a Sprite or whatever it is, right? But sometimes not all outputs are possible. Like, for example, if I look at this machine, can I get out a Diet Coke? Yeah, I think so. There's one right there. If I look at this machine, can I get out a bottle of water? Sure, there's one right there. If I look at this machine and say, can I get out a motorcycle? You laugh and say that's ridiculous, but not all outputs are always possible either. Right? Outputs would be your y values. For example, let me go back again here. Right here, let me do another function. Let's say we did a basic quadratic, which we're going to learn today, y equals x squared. I would like you to find me an input such that when you're done, you get -9 when you're finished. Can you make it so that -9 is my output? And you look at this and go, well, hang on a sec. When I square a number, doesn't it always make it positive? In a way, I'm actually asking you take x squared and somehow make it equal to -9. And then you'd say, well, let's square root both sides. And then you'd say, well, x is the square root. Hang on, I can't do that. Right? So input is what you're validly allowed to start with. Output is what you're validly allowed to end with. We call those domain and range. That being said, so far you guys have probably learned that this is what we say for domain and range. And the reason why is that if I give you a nice linear graph, and the linear graph looks like this, is there any x value that you can't type in? Like if you were to look at the x value here of 7, yeah, that works. What if x was -5? Yeah, there's a point there. So every x value is valid. What about y values? Well, y values approach it a different way. If I asked you where the y value is 6, you'd say the y value is 6 right here. Or is the y value -2? There's the y value is -2. Is this familiar to you guys, by the way? Okay, we're going to build on this today, and we're going to talk about how this right here is not always everything. And it really just depends on your graph. So, I think I can probably fast forward. We talked about this slide real quick, right? I think we did. This one is not a function then, because your domain did not fit properly. 0 tried to give -2, but 0 also tried to give 1. This is a domain problem. And like I said, computers can't reconcile this. This is why you get an error code. This would be like me going to the vending machine. I type in code A1, and I expect to get a chocolate bar and a thing of gum. I know that would be awesome when you like accidentally get 2 for 1, but that's not really how the machine's supposed to work, right? When you type in this code, you're only supposed to get 1 item back. Okay, so let me show you a couple last graphs and we'll move on to our new section here. Is this a function? And one of the easiest ways to tell if something is a function is to use what's called the vertical line test. Does this ring a bell? Vertical line test. Basically, the idea is make yourself a line. I can use my tools here. I'm just going to make a nice line like this, a vertical line, and slide that line across the paper. If it only ever crosses, like see here it's crossing there, and then here, and then there. If it only ever crosses once, then it's a function. That's not right. So as I slide this line from side to side, it only ever crosses, it never crosses this graph more than one time. But let me show you a graph which is not a function. Cut. This one's really cool. This is the Batman graph. And if you want to learn how to type this into your calculator, that's the equation for it, by the way. So if anyone's particularly ambitious and wants to make a Batman symbol on their calculator. Okay. But here's why this is not a function. As I slide this vertical line side by side, see how like right there, I have a problem. Because here and here, see how it crosses twice? What this means is that if you plug -5 in, -5 gives you -2, and -5, oh, that's actually +2. -5 gives you +2, and it gives you -2. That's not considered a function. Now, it's still a graph, but it's not technically a function. Does that make sense? The last thing that I didn't finish yesterday is this picture right here. I like this one. This one's kind of cool. Over the next year and a half of you guys learning math from me, we're going to teach you a whole bunch of different types of functions. I just thought this one was kind of cool because really a function is a graph. And if we can find a pattern that fits, it's a function if and only if as you slide your line across, you guys see how it only ever crosses once. Does that make sense? If we had a graph, I'm going to draw one more on here. If I had a graph that looked like this, you guys see how that wouldn't be a function? Because as you slide the ball across there, as I slide it across, it would have to loop back on itself. And that's basically what makes it not a function. So, sound good? Okay. I think that was it for last day's notes. So let's move now into quadratics. So our big goal today and tomorrow is I'm basically going to try to cover all of the -2 curriculum in 2 lessons. Okay, so hopefully it wasn't really that new. Like, it was more or less I pulled my grade 10 notes together, but I want to make sure we're all on the same page. Okay. Today, everybody learns about quadratic functions, and then if you're in -2, that's it. Okay. If you take 30-2, by the way, that's where Mr. Bonnet is right now, and he's showing the -2s like more functions beyond the ones you've learned for now. Okay. If you're going to take 20-1, you're going to learn about quadratic functions. You've already learned linear. And then later we're going to teach you about something called an absolute value function, a reciprocal function, and an inequality function. And so we'll just add to the list. Okay. But in general, the same things apply. We're going to find equations, we're going to find tables of values, we're going to find graphs, and we're just going to talk about the properties of those graphs. And where applicable, we're going to try to show you how these graphs can be useful in life, I guess. Like, for example, some of you guys in my chemistry class have already seen me show how we can use this sort of combining the skill to solve chemistry problems. So, wait, why don't I skip ahead here? Because we've already talked about functions being inputs and outputs. So this would be a linear graph, but do you guys feel like we can skip over graphing a linear one? Would that be okay by you guys? Okay, so let's not bother graphing this one here. Where should we start? Okay, let's start here. Can you guys find this slide here? Up until now, the only functions that you guys have been required to know is a linear function. And if I were just to kind of draw off here in the corner for a bit, a linear function is basically a straight line. Something like this, y equals 3x plus 4. Do you guys know why we call it a linear function? What is it specifically about this graph that makes it linear? the degree of 1. Now, if you look at this graph right here, you might say to yourself, where did you find a 1? But there is a 1. It's actually x to the 1 right there. We don't write the 1, but it's implied. Okay? And so linear graphs are defined by the fact that they are a degree of 1, and they're very straight line graphs. Our goal over the next couple of days is to talk about what happens if we give you a quadratic graph, which would be like a degree of 2. Now, there may be, after you do a squared variable, there could even be like an x to the 1. There could even be a constant term. What's the degree of the constant term, by the way? Anybody know? 0. This 4 right here really means that you have 4 x's to the 0. Have I ever shown you that? So like even if I give you the graph of x squared right here, it actually means that you then have 0 x's, and then you have 0 x to the 0s. Like you have 0 x to the 1s, and you have 0 x to the 0s. And most of the time we don't bother writing that stuff. Okay? But in theory, you can always write it in this format here. A certain number of x squareds, a certain number of x's, and a constant term. Now, I always throw this unit purposefully after our first unit because you guys already know a bit about quadratics. If I were to give you the quadratic x squared plus 5x plus 6, we already know how to do some stuff with this. You guys know how to factor these. Does that make sense? So really, quadratics as a graph now are really just us factoring polynomial stuff. Only rather than doing this skill right here, we're just going to look at what they look like from a graphical point of view. So here's the basics of what a quadratic graph looks like. If you guys have your calculators, follow along. I'm going to graph just a basic one here. So I'm going to split screen this thing. Okay, so hopefully you guys remember on your calculators all the buttons we reviewed yesterday. The first thing I got to point out, because someone already asked me this one here, if your graph is not working, you may need to go back up and take that plot and turn it back off, because you're not going to want that. Go ahead. Okay, turn that plot back off, because you don't want that on. Let's just graph just a really basic one. Let's graph x squared. This is about as simple of as a quadratic as you can get. Should I dim the lights a little bit? Would that help? Oh, I'm going to dim them a little bit anyways. Might help sharpen it up. Okay. How many x terms do you have in this graph? 0. How many constant terms do you have in this graph? 0. Yeah, it's kind of dumb to write it as x squared plus 0x plus 0x, like that, but this will work. And if you were to just do a zoom 6 to get a basic graph, this is the rough shape of a quadratic. It's kind of like a bowl or a dish shape. And in future slides, actually it looks like those are on my next slide here. I'm going to show you where this is actually really common, this sort of shape in everyday life. So maybe just stay on your slide here, but I'm going to show you some pictures here. Here's some pictures that I found of how quadratic shapes are actually very common in different places. For example, this is the St. Louis Arch. It has the quadratic shape to it. Here's another arch I found. You guys can kind of see that it's that same sort of shape here. Only, can you guys agree that this one is like facing up? This one's just upside down, right? That's all. I didn't realize this one until before. The inside of your dental palate is actually the exact same sort of U shape as a quadratic has. It's kind of cool. A flashlight will often emit light, and maybe you guys have heard this term before, a parabolic. Ever heard the word parabolic? That's actually the name we give to this quadratic shape. We call it, the name we give it is called a parabola. And so if you've ever heard the term parabolic, that refers to this sort of shape. Satellite dishes are often parabolic. Lights on your car, you might have heard of like a parabolic reflector. Anyways, if you ever heard that term before, it refers to this kind of like, it's not a U exactly. Like I would say that a U should go like straight down, curve, and then like straight up. And so like these lines right here should be parallel. They're not parallel, like it kind of goes out still. But if it has that sort of U shape to it, it's parabolic. When you guys eventually take physics from me, you'll discover that a lot of natural things are parabolic. For example, I found this guy here shooting a basketball, and it's actually, if any of you grabbed a progress log from there, it's actually the cover picture on it. where if you can see it, here is him shooting the basketball, and it actually has, if the ball went through the hoop, it has that kind of U shape to it. This shot I think is really cool. This is a time-lapse shot of somebody doing a snowboarding trick. And it's really wide, obviously, but can you guys see how it has that kind of like U shape to it? Long story short, that is the defining characteristic of quadratics. Linear graphs are straight, perfectly straight line. But quadratic graphs have a nice cool curve to them. They go up and they come back down, or they go down and come back up. It's basically like a U. So as I show you guys this graph right here then, that's kind of the concept we want to build on, is how can we modify and change this graph? When you guys learned about linear graphs, I'm just going to insert a new page, you guys would have learned that it was like y equals mx plus b. You guys remember what the m referred to? Slope? What was b? Y-intercept, yeah. And we could like modify our graph and make it so that a graph used to have this much slope. Well, then when I change it, it now has this much slope. This one is steeper. I can also change where the y-intercept was from, like, say, here to up here. We can modify the graph. My goal today, then, is to talk with you guys about, well, how can we modify a quadratic graph? For example, if this is a basic quadratic graph, one of the things we'll do is say, what if I give you x squared minus 8x plus 12? What if I start adding extra stuff to it? Now, what does it do to the graph? And you guys might notice that the new graph, it's still quadratic, right? Doesn't it still have that exact same shape? But it's in a new spot. It's slightly bigger. It's a little bit wider, perhaps, but doesn't it have the same base level shape? So that's my goal. So why don't we try an example? Do this side by side with your calculator. Let's try graphing this one. X squared plus 2x minus 3. So just get rid of all the old stuff. And in one of them, go x squared minus 2x plus 2x minus 3. You got it. X squared plus 2x minus 3. And this would be really typical for what you guys are going to do in your skills journal. Okay, I'll give you an equation, graph it. So, does it have that sort of U shape to it? The parabolic shape? Yeah, it totally does. Now, please do not spend a lot of time trying to draw this to scale. I don't care that much. Okay, so long as you label the key points, I'm good. So I would say the graph more or less looks like this. It cuts through about there, goes about that deep, comes up here. There, that's roughly my graph. Does that work? Okay, this graph has 4 key points, which I would like us to find. 4 key points. Now, some of them you guys have already maybe know. Like, for example, x-intercepts. Okay, how many x-intercepts does this graph have? It actually has 2. But think back for a second here. When we were working with our factoring, and I asked you to solve something quadratic, how many answers could a quadratic equation have? It could have 2. So there's really an x-intercept right here and an x-intercept right here. So I'd expect you to find them both. You guys remember how to find that in your calculator? Second, calculate the 0, and then you need to narrow it down the range. So everyone's calculator is going to be slightly different, but I'm going to make it go on this side here, and then scroll over to this side here, and see how it's going to find like a little narrowed down band to search in. Once I press guess, it'll find that this one here is at 1 and 0. There's the second one though. So I still got to do second, calculate a 0, only I have to like scroll the cursor way the heck over here. I have to click clearly on the left-hand side, clearly on the right-hand side. See how that kind of like narrows down a little search range? Basically what your calculator is asking you for is the domain is everything. That's what your calculator is saying. The domain is everything. Can you please narrow it down from everything to something a little bit smaller? Because, I mean, as smart as your calculator it is, it can't literally search every number in the entire universe. You get what I'm saying here? So basically you're saying look for everything less than like -5 or greater than -5 and less than -2. And somewhere in there, your calculator will find that you have an x-intercept of -3. That make sense? Did you get it to work? It's not working? Okay. By the way, call me over, guys, if you're struggling with calculator skills here. Okay, so you need to be on Zoom 6 so that you have a standard graph. That's the reason why. Okay. Anybody else having issues calculating that so far? Okay. Let me show you something cool here, by the way. Remember how I talked about in our first unit, we learned how to factor these things? If you guys can, just pause for a second. I want to show you like this big, like, it fits together moment. X squared plus 2x minus 3. We learned to factor this into x plus 3, x minus 1. Right? That's how you factor it. When it's equal to 0, we learned how to solve this. And x was equal to negative 3 and 1. When you factor and solve, you're actually solving for x-intercepts in a graphical format. It's two sides of the same coin. There's the algebra side, and then there's the graphing side. So this is why I always do the algebra first, because you might have been able to pick up on where these numbers came from if you know how to factor this. Oh wait, next point on the graph you should do. You should always do x-intercepts, okay? You should also do y-intercepts. And hopefully you guys would be able to recognize that right in there, you have a y-intercept. Now, y-intercepts are actually really easy to find without even using your graphing calculator. It's always the constant term. Okay? A y-intercept is characterized by what happens when x is equal to 0. When x is 0, you have a y-intercept, which is going to be negative 3. But I don't even need to use my calculator for this. Because if x was 0, 0 squared kind of is 0. And then when you add 2 times 0, it's still 0, right? So if you ever want to find a y-intercept, all you need to do is look at the last term, just like in linear graphs. So I would need to label this one as 0 and negative 3. So that's 3 points on the graph I would want you to know about. But I said 4. Okay. And the fourth one has to do with domain and range. Let's say I asked you about domain. The domain of this graph would be x as an element of the reals. There is no x that you can't plug in. Plug in 5. Sure. 5 squared plus 2 times 5, that works. Plug in 19. Sure, that works. But the range is different here. The range of this graph is not everything. Because if I ever want this graph to equal negative 7, I'm going to put a line across here at negative 7. Here's a line at negative 7. Did this graph ever reach negative 7? No, it doesn't. You know how when you use the quadratic formula, and sometimes you got the answer, there is no answer? Maybe this helps you visualize it. If I want this to ever equal negative 7, it can't. The graph doesn't go that low. So the really key point on this graph then is to figure out, well, how low does this graph go? And if you were to take a horizontal line and slide it up, hopefully you'd agree that right about there is about as low as this graph gets. And on this graph right here, that's this point right there. You guys see that? It's like the peak or the crest or the lowest point of your quadratic. We need to find that point. But I pointed out yesterday, some of you might already be ahead of me on this, that there are some tools on your calculator to find such a point. If you go second, calculate, look at some of the options on here. Any of those pop out as being maybe useful? Value, 0, minimum, maximum. Which one of those would be useful? Minimum, yeah, it's minimum. The reason why is that right here we have a point on the graph that is like as low as it gets. Does that make sense? So if you use the minimum search tool, you can find the lowest point on the graph, but you just have to know how to use the tool. So here's how it works. It asks you a question, left bound. Basically it's saying, again, look, the graph goes from negative infinity to positive infinity. That's too far for it to search. Your calculator wants you to narrow it down. So clearly put the cursor on the left-hand side of wherever your minimum is, like say right about there, and press enter. You guys see how it gives you that little arrow thing again there? Basically, you're narrowing down the search. Then it asks you right bound. Well, then put the cursor somewhere on the right-hand side. Now, don't do this. Why would this give your computer an error code? Did I actually go on the right-hand side of like the little loop right there? See the error there? So if I were to try to do this, my calculator would say that that's the minimum. But it's only the minimum because that's the lowest in the radius I gave it. You know what I'm saying here? clearly make sure when you do this that you go on the left-hand side and then go like around the loop. It doesn't matter how far you go. Like you could go all the way over to here for all I care. But it has to be this is on the left, this is on the right, and then press yes for a guess. And we find this point right here. This point is at negative. Okay, now everyone's calculator sometimes does this a little bit differently. Did anybody get something different than this right here? Yeah. This is where your calculator's trying to do some pretty crazy calculus. It's a computer, it can handle it, but sometimes for reasons that I'm not really aware of, it does something dumb like this and it says 999999996. Hopefully you'd agree that isn't that the number -1. So, and someone else's calculator might say 9999997. You might even see it be like -1.000001. So sometimes you just have to be smarter than your calculator and say this is -1 and -4. Does that make sense? Did anybody else get that? -1 and -4? Okay. Here's the important point then. This point right here we would then label on the graph right here as -1 and -4. But the reason we need this point right here is all for the -4. That -4 helps me with my range, because my range is this. Y has to be everything greater than or equal to -4. That's your range. Can Y get as low as -5? It doesn't get that low. Can Y get as low as -6? No, there is no answer. That's why when we learn about this in the quadratic formula, maybe that makes sense now. Why is there like a question that you can give me where I'd say there is no answer? Well, this graph does not get that low. So why is everything as low as -4 and up? So that's your range. So from now on, when you guys are doing graphs, if it's quadratic, I'm going to expect the following things. I would expect you to tell me a x-intercept, a y-intercept. I would also expect you to tell me a domain and range. I would also expect you to plot this lowest point. And it has a name, by the way. We call this low point right here. It's called a vertex. This lowest point down here is called a vertex. So if I ever talk about a vertex, either find me the lowest low point, or if I happen to give you a graph that's inverted and looks like, say, this one right here, you might want to find this highest high point. Okay. So it's either the peak of the graph. If we were finding that, what would we use, by the way? Yeah, use maximum, right? So either find the highest peak you can find or find the lowest value you can find, right? Either use maximum or minimum. And hopefully you can kind of already see that like this has practical real-life application if you're trying to find that. For example, if I were to graph this guy's basketball shot as a function for whatever reason I care about, right? If I were to ask you when does the basketball get 10 feet off the ground, if 10 feet off the ground is up here, you would say it doesn't. If I were to ask you when does the basketball get 7 feet off the ground, you would say, well, here's 7 feet off the ground. It's 7 feet off the ground right here and right there. Right? I could teach a computer how to shoot a basketball and land perfectly in the basket every time if I could map out its trajectory. Does that make sense? And I mean, nowadays, people are working on stuff like this in much more complex problems, like, for example, self-driving cars. Right? They need to be able to map out tons and tons of algorithms in split seconds and be able to recognize what sort of functions they notice. Is this something that's going to be a straight line? Is this going to be curved? And eventually you guys will learn about functions that look like this, or that look like this with like a V. Or in math, in chemistry today, I talked with you guys about how there's what's known as a reciprocal function. This was Boyle's law. Anyways, I'm getting ahead of myself. Any questions on this one here? Okay, let's try another one. I'll try to go a little faster because I went real slow on that first one. Let's graph this guy here. So same thing, just type in the equation. Negative x squared minus 2x plus 3. And then graph. And right off the bat, you're going to notice something different. What changed on this one? Is it still quadratic? Does it still have that U shape to it? Yeah, put that in words. Say that louder. Yeah, rather than having a valley, it has a peak. But is it still quadratic? Yeah, it's still quadratic. So here's the question I would ask. Compare the two equations we just did. This equation right here and this equation right here. What is different between the variables I gave here and the variables I gave here? Anyone notice anything different that might cause one graph to be right side up and the other one to be upside down? I did. And it's not just all of them. It's very specifically this one right here. See how the very, very first one is now negative? You guys have already learned about this in linear functions. If I were to give you y equals 3x plus 4, hopefully you guys know that it has a positive slope. But if I were to give you y equals negative 3x plus 4, do you guys recall that this negative sign means that it goes downhill? Essentially, what I'm describing here, it's not slope technically. The word I'm going to use is called leading coefficient. The leading coefficient here, leading coefficient, is negative. As soon as I throw a negative in front of the first term, it just makes the graph go upside down. Well, now that I've done that, I can do all the rest of the same sort of tasks here. So why don't you guys see whether you can beat me to it? Find me the x-intercepts, find me the y-intercept, find me the vertex, the domain, and range. Okay. I'll make a little list here. Tell me the x-intercepts, the y-intercepts, the domain, the range, and the vertex. See whether you can find all of those things there. I'll give you like a 1 or 2 minute head start, and then I'll start putting them up on the board. Yeah, I can let you in. Yeah. This is one of those things that you totally need to work along with us, eh? Does anybody else need a graphing calculator, by the way? Okay. If you can't get a hold of one, I'll see what I can try to do to help. I've got one extra one here. Can you guys share on this one maybe for now? But yeah, you definitely are going to need a graphing calculator over the next unit. All right, so here's my expectation. I would graph it. It would look something like this, give or take. Again, I don't really care whether you're perfect, but there are 4 points you should have. You should have this x-intercept, this y-intercept, this vertex, and that x-intercept. So I'm going to start solving them. Yeah. Okay, so you're going to want to press y equals right here, and you're going to go negative x squared. This one right here, there's x, yeah. Plus 2x. Oh, sorry, it's minus 2x, my bad. Minus 2x plus 3. When I graph it, hopefully it looks like this. Okay. So then some of the next buttons we did are second, calculate, and there's value, 0, min, max, and intersect. And they all kind of do different things. So I'll show you one of them here. If you want to use 0, there's an x-intercept right about there. So I'm going to put the cursor right about here. See how I put it? Actually, it's buried. You can't even see it. But see how there's like a little arrow there? It's pointing this way. Then I'm going to go over here. See how it's going to put the arrow going the other way? It's now narrowed down. It says it's going to find any 0 between there and there. And then it asks for a guess. You just press enter. And now it finds you that one. It is 1 and 0. That make sense? Okay, kind of play around with it a bit, and I'll come tutorial maybe later. Okay. Was everybody able to get all of the points up till the vertex? Okay, I haven't got the vertex yet, so let me do that one as well. This time, though, it's going to be a maximum because it's the peak, right? And then if you can do it properly, it doesn't really matter how far on either side you go, but hopefully you guys are able to do this. So, Okay, again, this is really dumb. For whatever reason, my calculator didn't regress it properly, but that's -1, right? -1 and 4. So my expectation then would be you've drawn me a graph, you've labeled all of the key points, and as you learn more and more functions, you have different key points. Each one has kind of different characteristics. So we've already done the x-intercepts and the y-intercept. Let's talk about these last ones here. What's the domain of this graph? Let me give you a different example here. What sort of x values could you not use? Could you use 7? -42? 1,000,005? Is there anything you can't use? Okay, so for right now, for the most part, it's almost always this. X is an element of the reals. Every value could be typed in as an input. But as an output, is y ever going to equal 5? What's the most it got to? 4. So you're going to say that y has to be less than, no, that's wrong. That's not right. Y has to be less than or equal to 4. Because 4 right here for y is as high as this graph gets to. Everything for y is now lower than that. So y is less than 4. This one right here, that was my y-intercept. So my y-intercept right here, which on your graph is right there, but the highest it ever gets to is 4. If I were to do this, let's say I made y equal 5. Do you see how y does not get as high as 5? If I made y equal 3, can y get as high as 3? Not only does it get as high as 3, I actually get 2 answers. That's okay. That's still a function. If y gets as high as 4, that looks like 4 is basically exactly as high as this graph gets to. So everything that for your y value has to be below that. Okay. My next bunch of slides are basically just theory to kind of describe what I've just shown you. So I'm going to blitz through these. Please stop me though if I lose you on a concept. This slide here talks all about the nature of your slope. Remember how you can have positive and negative slope? It's just we don't call it slope. That's all. Okay. Really, the way this works is you either have, I love this slide, either you have a happy quadratic or you have a sad quadratic. It's silly, but it works, right? If you have a positive leading coefficient, it looks like this. If you have a negative leading coefficient, it goes upside down. That's all. So in front of your quadratic term, if this is negative, it goes upside down. If this is positive, it goes right side up. Make sense? So that's what this slide is on. Okay. So this one right here, I want to go a little faster because I'm taking a little bit longer than I'd like to. Before we even graph it, make a prediction for me. Will this be a smiley face or a frowny face? Why? Okay, so I'm expecting a smiley face. Before I graph it, make a prediction for me. What is your y-intercept? 3, because this guy right here is my y-intercept. Make a prediction for me. What are your x-intercepts? Ooh, a bit more challenging. But don't forget, we can find x-intercepts by factoring. Can we factor this guy right here? Actually, I can't, can I? Because I need numbers that add to give 2 and multiply to give 3. I can't factor it. Hang on to that thought for a second. Let me graph it now. Let's check. Here I have x squared plus 2x plus 3. Now I couldn't factor it, could I? You know what, maybe before I press enter, I might even try one more thing. Let's try the quadratic formula. -2 plus or minus 2 squared minus 4, 1, 3, all over 2 times 1. Now this would give you 4, and then you'd be minusing 12. Would the quadratic formula even work? Is it where I'm going with this? I'm taking this quadratic right here. I'm trying to throw it in the quadratic formula. And when I did that, I get 4 minus 12. Can I do 4 minus 12? It doesn't work, right? Well, now look at my graph. How many x-intercepts does this graph have right here? It doesn't have any. It actually fits with our first unit. The reason why you get a quadratic formula that gives you no answer is because maybe this graph right here doesn't have x-intercepts. Right? So this one's actually really easy to solve. When I want to graph this, it looks like this. I don't even have an x-intercept to solve for. So I have a point here at 0 and 3. That one was hopefully easy. All I've got left to do is find the vertex. So find the minimum. Hopefully I'm going a little bit faster here. Go on the left. Go on the right. My vertex is at, let's call it -1 and 2. So what's the range? The range would be everything where y is greater than or equal to 2. Can it get as low as 0, though? Can't get as low as 0. That's why the quadratic formula failed us. And that's why you get that square root under like the square root right here. That's why you got a negative number there. Okay, so I want to kind of skip through this concept here, but you guys get the point I was trying to make? Is that this graph right here, the first one we did, it had 2 x-intercepts. This graph right here also had 2 x-intercepts, but it was upside down. What made it turn upside down? This negative number right here. This graph right here didn't even have x-intercepts though, right? And it's possible this graph is way up top here and it's not even solvable. So that's what I want to point out on this slide right here is that when you guys use the quadratic formula, there were 3 possibilities, right? Either you got 2 answers, you might have just got 1 answer, and then there was the answer, there is no answer, like it's unsolvable. Well, that would be like this graph right here. Where are the roots? Doesn't have any. So, did I make that point well enough? Okay, so let me do some more theory on our graphs here. These graphs right here, these quadratics, they have this point down here known as the vertex. Okay, and this base as the vertex is really such a key point because it helps us know how low or how high the graph gets. So logically, finding that vertex is really the key to knowing all about these graphs. One other thing I want you to know about is that these graphs are always symmetrical, always symmetrical. So if you wanted to, you could actually draw a line directly down the middle of one of these graphs. Hence, we call it a line of symmetry. That line, though, has to go through this vertex. Okay. Here's some more pictures I have here, just kind of showing us what some various quadratics could look like. Tell me something about this quadratic right here. What's unique about it? It's upside down, right? How do you make it go upside down? Negative leading coefficient. So this is going to be like negative x squared plus 3x minus 4. How do I figure out the minus 4? Your y-intercept is always the constant term. Now, I don't know that this is exactly the right graph, but the negative makes it go upside down, and the constant term gives you your intercept. This one right here, I know that it's going to be like positive x squared plus 3x minus 2. And I know that because this is like, say, minus 2 right there. The positive makes it smiley face. That makes sense? All right. What do I got left? Give me a sec. I want to see my stuff. Okay, we're almost done. Perfect. Okay, so why don't we actually, do you guys feel like you have what I'm trying to go for here? Do you guys think you could do this? I don't actually have anything new on this. You want to try one more? How about I do this? How about I end with this slide here? Let me do the last 2 questions, and then if you want to come back to this one here, we do this one. But like if you feel like you get the point, here are the main things you have to be able to solve for now. Could you find me the x-intercepts? Could you find me the y-intercept? By the way, what's the y-intercept? 6, right? It's right there. With the calculator, could you find me the vertex? The domain, by the way, is always x as an element of the reals right now. And then once you find the vertex, you find the range. If you guys feel like you can do this, let's move on. If not, can we talk later? Does that work? Okay. So here's the last thing. I need you guys to be able to, given like this sort of stuff now, we want to use this to solve something practical. So once you can figure out things like which way it's opening, where the vertex is, whether it's a max or a min, if you can find all these properties, let's try to use it to solve a question. So this is our last thing here. I might give you a word problem. Okay. Now, yeah, that's the first thing I hear. Everyone hates word problems. Okay. You just need to know what each piece of information in the graph represents in a real-world scenario. So let's start this one off by just graphing the equation given. Can you guys all see this equation here? Let's graph this guy. It's going to be y equals negative 4.9, and then it goes t, but let's just use x squared plus 6.8x plus 3. We're going to graph this guy. And as I do that, and I graph it, I get this graph right here. Anybody else have issues getting this one to show up that's following along? Yours are good? Okay, so let's talk about what's happening now. I haven't even read the question here. I just graphed the graph. It says a diver jumps from a 3-meter springboard with an initial velocity of 6.8 meters per second, and her height in meters above the water after leaving the diving board can be modeled by this function. Well, now look at this graph. It's like it's going up and then back down. If I were a diver, hopefully I don't kill myself here, about to dive off the diving board, what's going to happen? I'm going to go up and down. Isn't that what's happening right here? She's going up and down. Does that make sense so far? But the first problem is I don't need this whole graph. Yeah, t is x, by the way. This one. Does that help? Okay. I don't need this whole graph. There are 3 quadrants of this graph that are effectively useless. I don't need this quadrant, this one, or this one here, because I can't go backwards in time. And although I guess I could argue that she might go underwater, why don't I change my window size and make it go from 0 to, let's say, 3 seconds maybe? And in the y-axis, let's go from 0 to 10. Maybe just play with your window a bit to make it look nicer. So 0 to 3 and 0 to 10. And now when I graph it, does this not more or less look like kind of what you'd expect a diver to do? The diver is starting on the diving board, jumps up in the air, and comes back down. So far, so good? Okay, let's answer our questions. What does the y-intercept represent? Your y-intercept is right here. I want to take a stab at it? What is that? It's 3, but why is it 3? Because she's on a 3-meter diving board, right? Like, the reason why this y-intercept right here is at 3 is because just like me jumping off my chair, did I start on the ground? I started on, that far above the ground, right? So the diver is starting 1, 2, 3 meters above the ground. So the y-intercept is where she jumps from, right? Okay, what's the maximum height the diver reaches? Right? Like maybe as a coach of a diver, you want to make sure they get the maximum height they can because they have the most time in the air then to do all their tricks and whatnot, right? So how high does this diver get? Well, we now have a tool for that. So I can calculate the maximum. Where's the maximum? Now, it's not always a nice round number. Which one of these numbers here is the maximum height? The x value that I got or the y value that I got? Because I have 2 numbers, right? I have 0.693 and I have 5.35. Which one is her height? Y, yeah. So the maximum height they've reached, let's call it 5.4 meters. So she started on a 3-meter high diving board and got as high as 5.4 meters. It actually asks when does she reach that height? Well, you know how you find the when? It's the x value. It took 0.69 seconds, right? When you're plotting this graph is height versus time. So when she goes up and falls back down again, she reaches her peak point at 0.7 seconds. That makes sense? So I can find how high she got with my y value. I can find out how long it took her to get there by the x value. D. When does she hit the water? What's the math term for the point on this graph where they hit the water? X-intercept, yeah, right? This point right here is where you hit the water. That's your x-intercept. So all you'd have to do then is go second calculate the 0. Now this one's kind of tricky because of the fact that I changed my window size. So I want to show you a little trick here. You always have to go on the left-hand side. So I go on the left-hand side here. And then I'm going to move the cursor past where I can see. You guys see how the cursor is clearly off my screen right now? I don't even see the cursor anymore. I'm just watching my Y value. As soon as my Y value hit negatives into the negatives, I'll press enter again. Somewhere in between here is where that intercept is. I've just gone off my screen, that's all. And hopefully you'll be able to find that my intercept right here is at 1.7. So right here, 1.7 is how long it takes for the diver to hit the water. Make sense? Okay. Domain and range is a little bit different in this one here. You know how domain in the past I've told you is x is an element of the reals? That's not true. Because what is x on this graph? Time. Can I have -3 seconds? That doesn't really fit. And more than that, would it make sense for us to record this after 1,000,000 seconds? After 1,000,000 seconds, isn't the person like out of the water and dried off already? So we really need to consider only the part that's really relevant. I think I could start right here with a time of 0, and by the time they're done, they're finished at 1.7 seconds. So here's how I'd represent this. I would actually say that your domain is such that x is greater or equal to 0, but less than or equal to 1.7. I'm basically saying that this is like the domain has to be between 0 but no more than 1.7, because what happens at 1.7? She hits the water. Does that make sense? I have a similar issue with range. Should I go as low as like -5 or -100? That doesn't really fit, right? What's the lowest on this graph that's really logical? Where's the lowest point that she should consider? 0, right? Because what happens at point 0 for y? She hits the water, yeah. Okay. Well, then what's the highest point she ever reaches? Actually, we already did this, didn't we? Isn't the highest point right here? And didn't we write down that the highest point was 5.4 meters? So sometimes your domain and range changes, and we write it like this. This is the lowest you can get to, and this is the highest you can get to. And then your value is like between the two of them. It's like this is the spectrum you can get between. Last question, then you guys can start taking off here. This last question is more about predictive modeling. Okay, I've already given you guys the analogy, the example of like say self-driving cars, or if you're in my chem class. Hopefully I've shown you how if you can know how to use a graph, you can make a prediction. Okay, I want you to make a prediction here. When this person right here is 6 seconds into their jump, where are they? When this person is 6 seconds into the jump, where are they? Or 0.6 seconds, right? Now, remember 0.7 seconds was when they were at the very, very peak right here? I predict that 0.6 seconds is going to be right about here. But if I want to know exactly where it is, here's how you can use your calculator to solve it. Second, calculate. Use the value, yeah. I'm saying what happens when your time is 0.6 seconds. And it will then tell me, well, okay, at 0.6 seconds, you were this high off the ground. And so when we're able to find a way to model data into real-world scenarios, we're able to predict, we're able to use that data to, like I said, make a self-driving car. Because it's able to look out there and say, okay, this is this sort of function, this is this sort of function. It can make a prediction and say, I know the sensor recognizes that it's 10 meters away from the stoplight, and 3 meters away from a person, and 2 meters away from a dog. Right? And so it's kind of doing this sort of stuff, only like on a much more complex level, obviously. So, okay, quick summary, then you guys can go. Quadratics. Rather than being straight lines, they have this U shape to them. Either the U shape is a smiley face, or it's like a frowny face. Okay. I need you guys to be able to use your calculators and find me some key points. X-intercepts, Y-intercepts, domain, range, vertex, those sorts of things. Okay. And then our ultimate goal, use this somehow to solve some sort of word problem. So if you guys feel like you got the idea, take off. If you want me to do like one more example, if you still want to, then why don't we do that right now? So, yeah, Kevin, what's up?